In this third and final video dedicated to the content lifecycle management speed up work, I'm talking about query tuning, and in particular in the context of PostgreSQL. So here's the problem statement. A wrong table was joined as inner because the query planner had outdated table statistics. And of course, the solution is to update the table statistics. Now, if you have already understood what I'm talking about here, I have nothing to teach you. You can skip this video altogether. Otherwise, I'm a little bit sorry, but we have to go through some theory. How does PostgreSQL, or for that matter, any relational database management system, translate the SQL query from the SQL form to something which is actually executable, and how does it get executed actually by the database? That is a process that goes through several stages. Now, stage one is to parse the query. Now, you don't have to understand absolutely everything about this tree. But it's important that you recognize that the query that was just a string before is now a tree that reflects its syntax. So here we are talking about semantics, but only a little bit. What we're really seeing here is a breakdown of the syntax. So we have select, we have a reference to some columns, which is a star, so all the columns in this table. We have a variable of range, which is users, which could be basically a relation, so a table. We have an expression of equality between a reference to a column and a constant, and so on and so on. So this first part is really, I would say, mechanical. So there is a parser, it does its job in a deterministic way. We get one string broken down as a syntax tree. Nothing really fancy, nothing different from your favorite programming language. Now, after parsing, this tree is transformed into another tree. And this second part of the process is called analysis. And here we have the new tree, which is called a query tree. A query tree is different from a parse tree because it contains elements from the database that's being queried. So in this case, for example, you can see here that Postgres has determined what star is. So this is the number of, this is exactly the list of the columns that are interesting here. Other than that, this tree is an expression of what is expected by the user. It doesn't really tell us how Postgres is going to perform it. So it says basically nothing about the algorithms that Postgres will actually apply in order to execute the query. It just says a more complete, if we want, version of what the user really wants, which is the query basically. The next step in the process is called planning. And planning is where Postgres turns this tree into an actual tree of operations that can be executed on the disks, on the memory of the database management system, and that can actually carry out the computation and return the result that's expected by the user. And it may look like this. So here we have a tree, which by the way is much simpler, which contains operations that are really executable by Postgres. So a sort operation, a sequential scan of a table on disk, a limit operation. So these are really functions that are implemented inside of Postgres. And Postgres has determined that this is the best plan among all of the plans it could explore. So basically, one of the main differences between this part of the process and what was before is that this tree can be turned into many different plans, not just one. Every plan has a different cost, and here you can see in every node that Postgres has computed an estimation of costs. And at the end of the day, the planner will pick among all the possible plans the plans which is cheaper to execute, or at least expected to be cheaper, because nobody, including Postgres, can know in advance which one will actually be the cheapest. But it can try to get there with a heuristic, can try to guess a little bit. So the planner is the most complicated component in this process. It's the most difficult to understand and to analyze as a programmer, to use correctly. But here is really the key of Postgres performance: the ability of finding the best plan given any kind of query. So once again, to wrap up the high level, this is how a query is executed. First of all, a parsing happens from raw SQL to a parse tree, then analysis from the parse tree to the query tree, then planning, which turns the query tree, sorry, there's a typo in there, into many plan trees, and from those, one which is the optimal one is actually selected. So you can imagine all possible trees are created in here, and the best is picked. Actually, it's not exactly like that under the hood, but yeah, you can imagine the process going like this. So this is, by the way, the reason why so many queries can be formulated in different ways and still yield the same result and still be executed in the same way. For example, if you look at this particular one, we have two join operations. What if I join the tables in reverse order? Well, Postgres will most likely execute them in the exact same way and produce the exact same plan, because among the possible trees, planning trees that can be generated, there will be trees that contain other table as the first table that's joined, or yet another table has the first table that's joined. And depending on, for example, how many rows are contained in each one, it might be beneficial to join one rather than another first. Or, for example, applying the where conditions in a different order. So, for example, filtering by my table name less than b before filtering the other table, because maybe this is a condition which is much more restrictive. So when you're writing your SQL, you can formulate in different ways, knowing that the planner will still try to get the best plan, which might reshuffle things up a little bit. There is one physical operation that Postgres has to use, which is join, which is particularly important. And we have to do a little bit of extra theoretical deep dive on how Postgres can execute joins. What are the types of join algorithms that Postgres knows, and how the planner can decide for a certain join type or another join type. Why? Because this is important for the particular case that we are optimizing in the content lifecycle management. So, planner is doing its job. It's translating into plan trees, has to do some joins, has to choose the best join algorithm depending on the situation. Which algorithms are possible? I will name 3 here. The most basic one is called the nested loop join. It's just 2 for loops, one inside of the other. Postgres will scan each row in the outer table. The first table, it's called outer here just because there's an outer for loop. For each row in the outer table, it will scan each row in the inner table, and it will evaluate the join condition. If the row that we are looking at in the outer table and the row we are looking at in the inner table satisfy the join condition, then this is a valid tuple to be added to the result. Otherwise, this can't move on. This is the most basic algorithm. If there are, there is an important thing to note here. Which table Postgres chooses as outer and which table is chosen as inner makes a difference. Imagine that you have the outer table having many more rows than the inner table. In this case, you will have to scan the inner table more times. So in general, it's convenient to pick as the outer table the table that has the least number of rows to limit the amount of scans of the inner table, because scanning the inner table is generally cheaper. So even when choosing a certain algorithm, choosing the order, and I don't really mean literally the order of joins, because this is not relevant, doesn't change the result, but the assignation to outer and inner table does make a difference, and the planner tries to exploit that difference to get to the cheapest possible plan. Second join type is called a hash join. It can only work in a situation when Postgres can calculate a hash over the attributes that compose the join query. If this is possible, or maybe the hashes already exist because of different parts of the plan, because hash indexes have already been pre-computed for whatever other reason, then the hash join algorithm can be used, and it's much faster than nested loop in general. It works in two phases. Phase one, a hash table is built with all of the attributes for the join condition for the outer table. And then for each row in the inner table, the hash of the same attributes is computed and looked up in the outer table hash table. So looking up in a hash table is of course very efficient in the general case. So the hash join can be quite a lot faster. Of course, Postgres has to counterbalance the need to build the hash table, which also consumes time and CPU. Third type of join, merge join. This is a little bit trickier to explain in words, but basically both the outer and the inner table are scanned at the same time, and we exploit the fact that both the outer and the inner table are already sorted. Again, this is something that might or might not be the case in the particular query we're looking at. Maybe Postgres determines that sorting the tables before merge joining them is less expensive than, for example, running a nested loop and accepting the fact that the tables might be in different order. But if this is possible, it's much faster. Now, instead of going through this, I will just show you a very nice GIF animation that I found that explains the algorithm. So as you can see, both of the tables are scanned at the same time, but interleaved. So basically, we start with pointers to the first element, and then whichever advances is interleaved. And we use the fact that they're both in the same order to catch all the matches. I will put a link to this GIF and a more extended explanation in the video notes. But what you have to know is that merge join is in general the fastest join available when the input is sorted. Now, after all of this deep dive in the theory and how Postgres planner puts together operations and how joins in particular work, the most important thing to keep in mind is that the planner will choose the best plan via some heuristics, like how much memory do I have available, how much CPU time does a certain operation cost approximately, and statistics. As we have seen, it's important to know, for example, how many rows will be in a certain table, how many rows will be filtered out by a certain condition. And in order to estimate that, the planner uses some statistics that are that Postgres keeps computed for every table every once in a while. So there is a daemon which is called the auto-analyze daemon, and this daemon, whenever CPU time is available, will go through tables and refresh their statistics to know how many rows are there, how many rows are already deleted, how many rows contain a certain value or the other value or in this range. Of course, problems may appear in case those statistics are not very updated. So if they're very outdated and the statistics do not reflect the actual content of the table, then the planner might do bad choices. And bad choices might mean very bad query runtime, which is exactly the case that happened here. How can one see which exact choices the planner does for a certain query? There is a command in Postgres which is called explain. And for example, if I run it, I can run it on this example query here in this insert. Here I'm using DBeaver, which is a nice point and click database explorer. What I can do is to execute it with explaining the execution plan. And what Postgres will do is to output the query plan, which, as we have seen, is a tree. And here we see all the various physical operations that the planner has decided upon, and ultimately Postgres has actually executed. So here we can see there's a nested loop, there's a merge join, there's a sort, another nested loop. So many of the friends that I've talked about before. Now this form contains all the information. It's not very easy to see. So there is a nice tool, which is this one. It's called PEV, PEV2 in particular. And it will output the tree in very nice tree form, and you're able to expand each node and get more information about it. So it's very, very nice to do investigation over queries with this tool. We have instructions to run it, so highly recommended. What we are seeing here is the plan of the slowest query in the content lifecycle management, and in particular, here we can see that there are those brown boxes around here, you know. And for example, here we can see that the planner has underestimated the number of rows that were expected to be processed by this particular aggregate operations by a factor of 1,500. This is pretty bad. This means that the planner estimated a much lower number of rows going through this function. And chances are this plan might not be optimal. You can see the same here for this sort. You can see the same here for this nested loop. And actually, if you look at the entire runtime of this query, you can see that the vast majority in here is 16 minutes. So the 99% of the time is spent in this particular aggregate function here, which is part of a nested loop. In this case, the nested loop shows another nested loop as the outer table and the aggregate as the inner table. So if you remember, one should always pick the outer table, which has the least number of elements. But here, the number of rows was underestimated by a factor of almost 5,000. Here, it was also underestimated, but much less. So basically, the planner has inverted the tables here, and it picked as the inner table the one that was actually smallest. And this determined the fact that that it took a lot longer to compute this aggregate because it had to be computed a lot more times. In fact, here I have ready the plan for the query after the patch was done, and so the problem was fixed. And you can see there is still a merge join here, and a nested loop here, but the order is reversed and the outer table is actually picked correctly. Now, the planner is still a little bit off. Here you can see it's off by a factor of 350. Here you can see it's still very off by a factor of 1,500, but still a lot better than almost 5,000 times. And indeed, the total query ran for about 700 milliseconds. Of course, this is something that could be further optimized, but it's a far cry from the 16 minutes that we had before. And now the question is, how could we convince the query planner to output this better plan? And the way we did it was to force Postgres to update the statistics that were very outdated for a particular table. So the patch is pretty straightforward. This command analyze forces the recomputation of statistics for a certain table. This is the particular table that was critical in content lifecycle management. So we are creating clones of channels, so creating new channels, and we are copying over a lot of packages in them. And this table contains the connection between channel and package. So this is a table that gets populated extremely fast during the execution of the build and promote operations in content lifecycle management. So just forcing Postgres to reanalyze this table and to recompute the statistics for this table at the appropriate point in time, which happens to be in the famous align environment target sync method after having aligned the errata. If we force the analysis here, then the next method, which is exactly the method that calls a slow query, becomes much faster. Why? Because the query now can rely on the planner to do a sane choice for the plan because it has updated statistics. Now, there were a couple of small complications in order to get especially this plan here. Because if you run the query at any point in time, as we did before, this is exactly the query that's problematic, by the way. You just run it. We have to clear the table before we do that, otherwise we get constraint violation. But anyway, it will take a few milliseconds. So here, half a second more or less. And this was puzzling because it seems to contradict what we see from the provider. So in the provider, this query is very slow, but then I run it in the DBeaver 1 second after, and now it's very fast. Why? Because between the time when the query was ran slow and the time where the query runs fast, the auto-analyze daemon would have analyzed the table. So the problem was to anticipate that point in time. It was a little bit tricky to get this initial plan because this query in the original code, also in the current code of current lifecycle management, is called inside of a store procedure. If you run a store procedure and you ask Postgres to explain the store procedure, it will not go in the individual queries, so you don't get a meaningful plan out of a store procedure. So I had to do a little bit of a hack that I have here. Basically, what we had before was a single mode query call to a single store procedure. If you look at that store procedure source code, it's this one. What it does is the delete query we've seen before, and then the insert query we've seen before. and 2 other quick queries. So what I did in the patch was to remove the store procedure call and to replace it with a call to delete, a call to the insert, and the other 2 small ones here. So that at this point, what I could do is to use, here I have another note file, the auto-explain feature of Postgres. And that would result in logs such as this one here. The log will contain all queries that exceed 1 second in duration together with their plan already in JSON format that one can load in PEV and then get this nice visualization, figure out what's actually happening. So once you have this trick of unbundling store procedures, you can get meaningful logs from auto-analyze, and then you can really see what's going on at the query level. And once I had this plan here and the plan for the first one here, I started to look at difference and figure out why it was so slow, and I simply tried analyzing the table at the right point in time, and that did the trick. So yeah, this was the last part, and with this I think I concluded the explanation how to speed up this particular code path by a factor of more than 200. And I hope the same techniques will help you next time you are facing a performance problem with your Java and Postgres code. See you next time.